All right. Okay, I'm switching gears today because I need to go through the instruction set and a little bit of the background, because tomorrow I've set up a lab that you're going to be doing using the development board. So before we do the lab, and as I mentioned before, the microprocessor that we're talking about hardware-wise is the 8086, 8088 family. Software-wise, we're talking the 8051. So this semester is a little bit confusing because we're kind of switching gears down the road here. So I'm going to be looking at, I'm switching gears a little bit to well, maybe we'll. Okay, let me kind of go through here. So I'm going to be going through the instruction set on the 8051 today, and I'm using the same slides I use for the microprocessor class because they're using the microcontroller course because that's the processor they're using. Both these classes use the 8051 for the labs that they're. So okay, so we're going to be looking first off. We're going to go through the addressing modes. There's 8 different addressing modes. There's actually a lot of material in today's lecture out there. Some of we've talked about before. Some of this is new for this particular class. And then we're going to be looking at the instructions, the actual instructions for this. And we're looking at this strictly in assembly language mode that they're. So as we look at this right here, these are the addressing modes right there. Some of these addressing modes are strictly for jumps or calls, and some of them are for accessing data. Then we've got our instruction types, and there isn't that many instructions for this particular microprocessor. Actually, from a software standpoint, you guys got a little bit luckier than the last semester, because last semester the 8086 actually has a much richer instruction set, which meant that there were a lot more questions that we could come at from the software side out there. So as we look at this right here, first off, a computer instruction is of the type, you have the instruction. This in assembly language, this is usually something like a move or a jump or an add or a multiply, but that's what we want to do. And it's usually a 3 or 4 letter word, might be two letters that are mnemonic that may or may not look like English. In most cases it does not. In some terms does it look like Basamalayas. So it looks like it's English there. Now this is reverse of normal thinking right here. This is reverse of normal thinking, because the data moves this way. It moves from right to left, right there. Normal thinking would be move from A to B, but actually the instructions move into A from B, right there. So as we look at it there. Now, a computer instruction can be, the instruction itself, it has to be 1 byte for the instruction. Then we may have 0, 1, or 2 bytes for the operand. The operand is what's back here. Some instructions do not have an operand. An operand is what you're going to do the instruction with. In other words, if we have a move instruction, we have to tell it move from where to where. Right there. So some instructions, including the move instruction, if we're moving from one register to another register, we may not have to have that because the move itself will contain that information. That there. So that there. The operand can be the data itself, and that's usually denoted by a star, the number sign or a hashtag. A register, that's usually a keyword such as R0, R1, A, B, or C. It could be a memory location. In other words, it could be 1, 2, 3, 4. 4 hex, that's a memory location, 1, 2, 3, 4. Or it could be a port, which also looks like a memory location, but it could be like P1 or P0 right there. So we can look at those right there. So that's what a typical instruction is going to look like. And we're going to be writing instructions. Let's see, your tutorial section's tomorrow, right? So tomorrow you're going to be handed. Actually, I posted it about an hour ago online the lab for tomorrow. But before you start the lab, I'll actually give you what the solution looks like. That there, I'm not going to give it to you in paper, but I'll show it on the screen. That there, it's not very good there. Okay, this is what the 8051 looks like internally. And I know I talked about this before, but let me just kind of review. We've got the ALU, which is the heart of this. That's the arithmetic logic unit. That's what executes the instructions. Coming out of the ALU, we've got the program status word. That includes things such as the carry flag, a zero flag, or a number of different flags. Now, the 8051 is completely different than the 8086 in the respect that addressing is completely different. Because the 8086, as you recall, had one address space, and it went from 00000, 5 hex numbers to F right there. The 8051 actually has multiple address spaces. It has what they call the code address space, which is that there we have our code address space, our code, and we have our memory. And I'm called data memory. Right there. Data memory. And they share the same, we can have 2 address zeros here, for example, right there. They are 2 separate streets. If we want to look at streets, 2 separate buildings. For the 8086, we had 1 building. We had 1 street. Everything, this part could be code, this could be data, this could be more code. Here, all of our code is here, right here. And there might be some data. And I'm just going to put the word some here, some data right there. There may be some there, and we'll talk about that here. This is all data memory. Now, in case of our 8051, the code memory is typically much larger than the data memory right there. So, as we look at this right here, we have also a stack pointer. We'll talk a little bit about the stack pointer. We have a B register, which is the other register inside the accumulator. This is our A register. So we have 2 registers, A and B, right there. Then we have our static RAM right here, inside there. And with the Core 8051, that's only 256 bytes. It's not very large, right there. And we also have, we'll see in a minute, another memory block called external memory. So we actually have 3 different memory for the 8051. The 8086 is a little bit simpler. It only has 1 memory to worry about. And we address everything. The 8051 has 3 different memory spaces. Code, internal data memory, which is this right here, and then external. And for our particular chip, we got external that's actually internal to the chip. That really confuses. That there. So as we look at this particular one here, that there, and then we've got down here, I'm not going to get into this much detail here, but we've got our memory interface. We got our special function registers. This particular microcontroller uses the special function registers to control the microcontroller. That's there. So the special function registers, we'll be talking a lot more detail about those probably in the next week, probably after the break. We may touch them a little bit on. We're going to touch a little bit on them today and tomorrow, but we'll get into these in more detail. The special function registers is really where the key of this right there. So the rest of this, I'm not going to get into too much detail. The interrupts are down here. We also have down here our logic control, our power control register. That's to stop or idle, put the processor in a shutdown mode to save battery life. So this is all internal to the chip. Now we're not going to dwell too much on that, other than the fact that we need to know that there's a program register, There's also the program counter incrementer. That goes back to that previous discussion right here where I said you could have, each instruction could have 1, 2, 3, or 4 bytes attached to it. Or excuse me, yeah, 1, 2, or 3 bytes attached to it. So we need to know how much we want to increment our program counter, because that keeps track of where we're at in our program. And we'll see some of this tomorrow. I'll run through this as we do the lab. I'll show you how to see that on the screen where we look at these registers. Okay, this is what our memory looks like, and as I mentioned before, we have 3 different memory spaces that we have to be concerned with. This is our program memory right here. That goes from 0 all the way up to about 2F there. This actually is our flash memory right there. That's when we write our code, that's where it goes. When we download our code into the board, it goes into this flash memory. Over here, we've got our data memory. This is our internal data address space. Now, we only have available to us the lower 128 bytes, typically, right there. And of that, some of those are bit addressable, some are general purpose registers, and some of them are for just general addressing. We don't have a lot of memory space for RAM on this chip. This is a microcontroller. It typically doesn't need much address space. The upper 28 bits there are specially reserved for the special function registers. Now, we could use those for some applications if we don't use those special function registers. But as it turns out, the Silicon Labs and most of the new 8051s out there have added so much junk, or I should say junk, usable peripherals to the microcontrollers that we need all these special function registers to control the add-ons. The original 8051 didn't have much in it. Remember, the original 8051 is, vintage 1981. It's been around. It came out when I was a student back in the dark ages. When the dinosaurs still walked around KL and they hadn't built any of these buildings yet. Back there, so it's a very old chip. That particular chip back then didn't have a lot of add-ons, so there wasn't need for very many special function registers. So we could, back then, you could use probably about half of the 128 bytes. Now they're pretty much all used, and I'm going to go through a table where they're used, show where they're used. So, but internal to the 8051 that we're using, we have this external address space, data space. Now, this here shows 4K right there. Now, I don't remember what our particular chip has on it. We can look that up. It's plenty, but this particular chip was based on the F020, which is actually one of their lower end chips. It has 4K of RAM built onto the chip. The only thing is that we have to treat that as if it's external memory. And this is where it gets confusing, because this is the external data space. This 4K is internal to the chip. It's built onto the chip. We don't have to wire it up or put it on or add to the chip. It's built into the chip, but we have to call it from a software standpoint external. So this is why we now have 3 separate address spaces. We have our data memory that's in the original 8051 core, and that's only got about 256 bytes of that. Half of that is used up. We can't use it. So we only got 128 bytes essentially to play with on the original 8051. We've got our flash memory, which is plenty. That's our program memory. Now we can put some code, some data into that there. Remember, what's in our flash memory though, we can't change at runtime. So typically, if we're going to put anything in flash memory, it's going to be a lookup table, tax rates, or sine and cosine tables, or square root, square tables, things that don't change, because this is programmed only when we're connected to the system. This is our program, has to go there. So anything that's going to go into here has to be generated at the time you write your code. Everything on this side here is RAM. Right here. That's program. That's memory that we can change at runtime. That contains our data, our scratchpad. Everything on this side here is we treat it as ROM. It's read only at the time we run our code. Right there. Now, the fact that it's flash memory that can be erased and reprogrammed, that just helps with the development stage. It doesn't change the way that we treat it when we're writing our code. It's still going to be built into the system and we can't change it at runtime. Now, remember, flash memory does have the capability that we can update the firmware at a later time, right there. We can update that firmware later, but usually, has anybody ever updated firmware in anything? Your cell phones, I'm sure you have, right? The Android is usually, or actually Apple OS is actually firmware, and you would download an update. If you updated iOS 8.1 now is the current up there. Of course, those that had the 16 gig phones had trouble with that when it went from 7 point whatever to 8.0, but you download it into the flash storage space, and then it reprograms the flash memory in the phone itself. That's a firmware update. So anything we build with this processor, we could put in the software to do a firmware update on it. That there, we could handle that. That there. We won't learn how to do that this semester. That's a more advanced topic. So again, we have program and data share the same address space, are accessed through different instructions, and that's also true with the external RAM. External RAM is only accessed using the move external instruction right there. There's a special instruction for addressing external memory. Okay, the internal memory right there, we have these four are our register banks, R0 through R7. There's 4 different banks. You have to specify which bank we're going to use, and you'll see that tomorrow when I go through our sample code. By default, we're going to use bank 0 right there. But we'll simply say that we're going to write our code, and we'll say using 0. In other words, bank 0. That means if we use bank 0, these other, let's see, there's 32 instructions there. We lose 8, so you're going to have 28 instructions. There are 24 instructions available. So there's 24 memory locations that are available for general purpose operations because we can switch our banks. Now you can switch banks mid-code too. And you can have some routines that use one bank and some parts of your code that use a different bank. If you do that, then of course you can't use those banks for other things. So this is just one of those things you got to be careful as you write code. If you write in C, the compiler usually takes care of that there. Locations 20 through 2F, these 15 and 16 instructions are also bit addressable. We have instructions where we can set or clear a bit right there, and we can address memory bit location 42, which happens to be bit 2 of location 28. So we can address these by bit if we want to, right there. And then these up here is our general purpose RAM from 30 to 7X is just general purpose RAM for whatever we want to use that there. Generally, in most cases, you can start at 20 if you don't have anything addressable, or you can start at 30 if you want to use the bit addressables. The bit addressables are typically used for things like Boolean flags, true or false, like that there. So, that there. Then we end up with now our special function registers. And as I mentioned before, between 8.0 and F8, which happens to go to FF, and I'll talk about going this direction in a minute, all 128 locations are used up right there. Right there. So this happens to be a table that uses all 128 locations right there. this first table right here, these are bit addressable. Right there, that's what it says here. It's set there. So we can address port 1, bit 3, for example. So in other words, we can address port 1.3 right there. That's a bit addressable memory location. So our I/O in this particular case is bit addressable right there. Now, I should also kind of throw out here that this table is a generic table. It happens to be for the F020, which has 4 ports attached to it. So it's got port 0, port 1, port 2, port 3. Our chip does not have these 2 ports. Right there. So, we could use those locations if we wanted to. The problem is if you use those locations and Murphy's Law, which I probably don't have Murphy's Law, that says anything that could go wrong will go wrong. And then there's the add part at the worst possible time. You design a chip using a chip, you realize later it's too small of a chip, you have to go to a bigger chip. So then you go to a bigger chip that does have ports 1 and 2 than that there. So it's typically you would not use anything on this table, even if it's free. Right there. And besides, we got that external RAM, that we've got plenty of RAM. So RAM is not a problem for most of our applications. It was a problem in 1980. It's not a problem today. Right there. So as we look at this here, we have all these special function registers. Now, this starts at location 80, 81, 82, 83, 84, 85, 86, 87, and then we go to here 88, 89, and we go across here, and you can see the 19, 2A, 2B. So these all start with 8. These 2 start with 9. There's 2 rows for each, for the 8. That there. So if we look at this particular one here, this location here happens to be AC, and that's the analog mux 1 select bit, right, or byte right there. So each one of these locations controls a particular peripheral on the 8051, or is the peripheral. So for example, we got ADC0 control register right there. That's the analog digital converter right there. And then here we got ADC0, and we've got the high and low registers for that there. We see this is PCA, where's ADCs? I'm trying to think, because this is our DACs, or digital analog converters, which we don't have. Oh, here we go. Here's ADC0, our low and high order bytes for it there. Right there. So we've got, this is part of the control register, but we've got various ports all dealing with analog digital converter 0 right there. As you can see, we've got 1, 2, 3, 4, 5 bytes required just to operate the analog digital converter. 1 byte to say which direction we want it to go. We can multiply it. We can do some stuff with it. We have to read our data. It's got a high order and a low level byte. So we have all kinds of information that there. We've got our ports. We also have our port controls. Right there. Here's our P1. That there. These are our 4 controlling our outputs. Right there. Whether we want to push-pull output or open drain output. We also can set these up as analog ports or digital ports. So, as I said, as we look at this particular chip, going back to 1980, there wasn't very many of these 128 bytes used. Now, pretty much every one of these is used. We've got 1, 2, 3, 4, 5, 6 empty bytes available on this particular family. Everything else is used. And the reason it's used is because they've added so many peripherals to this chip that we have to control. So, and if you look at the data book for this particular IC, you'll find that it's about 350 pages, of which 200 plus have to do with how you write to each of these control ports or each of these special function registers. This is the biggest part of this processor. It's learning how to use these special function registers. If you figure out how to do that, you understand this chip. very well. We're going to just touch the surface this semester on this one right there. Okay, getting into what we want to talk about today is our addressing modes. We have 8 addressing modes. One is we're dealing from registers, right there. That's internal to the original 8051. Then we can do direct. Direct, this happens to be a memory location. Right there. Indirect means that R0 contains the memory location, contains the address. R0 has the address. Immediate means that we're going to move 8-0 straight into, or add that straight to the accumulator and store the resulting accumulator. Relative means that we're going to simply jump ahead or behind plus minus, I'm going to say plus minus 127 bytes right there. That's usually used in a short jump, or if we're going to do a relative with jump. This is used for jump commands. These 3 are all used for jump commands right there. Right there. Right there. And then we've got an absolute jump where we apply 11 or 12 bytes of the memory location. Not all of them. In other words, we're jumping within 1 page or 2K of K there. And the long jump means we're going to give it full 16 bytes of the address. In other words, then we'll look at these. And the index means we're going to move, and we're going to take the address that's contained in A, and we're going to add that to the program counter. So we're going to use, so in other words, there's 2 parts of the address. Part of the address is in the program counter, and the other part's in A, and we just add those 2 up. Right there. So these are our addressing modes right there. And they're fairly straightforward. You got a slide on each of these right here. You know, register for addressing involves information between registers that's within. These are typically done within 1 machine cycle or clock cycle. Let me get that straight. A machine cycle, instruction cycle. There's a clock cycle, there's an instruction cycle, and there's a machine cycle. An instruction cycle is roughly 3 machine cycles. So this has got 2 megahertz clock. It takes about 3 clock cycles in order for this instruction to operate. And that's part of this week's lab. I'll discuss the lab tomorrow. Now, our registers banks between R0 and R7 are in those banks 0 through 3, which are specified prior. And as we look at tomorrow's lab, you'll see we specify that we want our code to start at such and such place in the data in the data memory, and we say using what register bank. Right there. Direct addressing means that we're going to move and we supply the memory address or abbreviated name. Now P3 is defined in this particular case in the C8051F028. We're using the 850, so we will include in our code a file called C8051F850.inc that specifies all these special function registers names, so we don't have to look them up in the table to know where they're at. Right there. So here we're going to transfer the contents of memory location 20 to A. Right there. So anytime you see a number without anything in front of it, that typically tells you that that's actually a memory location. That's the default addressing mode, is direct addressing. Indirect means that we're going to store an address in R0. Store the content of the accumulator in the memory location pointed to by R0. Should have an 8-bit address. Remember that these instructions only work with the move with indirect only work with that 128 bytes on the processor. Here we have a move X. Move X is talking to that 128 or that 64K location that we can use, of which 4K is on the chip. So we'll say 4K that's on the chip. That there, and therefore we have to supply the 16-bit address, so we store that address in the data pointer, which is a 16-bit location. The R's, in this particular case, R0 is only 8 bits, but since this is a move, the move uses the 128 bytes internal. Right there. The move X uses the external memory. It just so happens that the external in this case is actually in the chip itself. So it's external, internal, I don't know what's the term, internal, external memory, but it's in the chip itself. That and one of the reasons they did this, and this really gets down to a lot of things, is that the 8051's a old processor, and there's lots of compilers out there for it. We're using a compiler called Kyle. Kyle is a company that writes compilers that takes our code, whether it's C or assembly language, and converts it into machine code. And as long as they stay true to the original 8051 flavor, then they can use any 8051 compiler. As soon as they go away from that, then you have to design a custom compiler. So since the original 8051 only had 128 bytes of general purpose RAM, that's all that any of these copycat chip manufacturers have done, because they didn't want to write their own compilers. They wanted to just go out and use the existing compilers. And there's about 3 or 4 different compilers we could use with this chip. We happen to be using the free Kyle one that they give us with this chip. There's also one called SDCC, which is a open source, which means it's free, but it's not as well supported. Kyle itself, if you buy the full-blown C compiler, it's about, the last I checked, for a commercial company to buy it, it was about 3,000 USD, which is somewhere in the neighborhood of about 10,000 RM. And that's for one copy, one desktop. It's quite expensive. Now, for academic use, like what we have in the classroom, they give us free with the software a very stripped down version that we can write about, code that's, say, somewhere in the neighborhood of 1K size, 2K size, which is which we're not going to blow past that in this class. I have had senior design students in final year papers design systems where they've blown past that, and they've had to come and check out the full blown software, because we bought a version, one copy for the department to use for that purpose. I don't Unikey I don't think has a full blown copy. I have one copy that I got a license from that I can get a copy licenses for the full blown version. As it turns out, they will give them to the universities now for free, but you have to apply for them. There's a process you go through. It's not very difficult, and it's only good for Silicon Labs chips. Silicon Labs has got a deal where we can get it. I'm not going to bother, because the poor technician would have to go through and get a license for each computer and install it separately. It would take forever. Here, she just takes the one installation and installs it on these machines. But regardless, that's why they stuck with this move external. 1980, which was roughly 35 years ago, that was truly external memory. Now, in order to stay current with it, so they can still use the old compilers, they still call it external memory, even though it's internal to the chip. Okay, immediate has this little hash mark there. Yeah. The hash mark means that it's literally what's after that. Move the number 30 hex into the accumulator, right there. So the default, and that's another confusing place where I'll get some of you on the final exam. I'm sure is that the default memory is the direct. That has nothing in front of it. Notice there's nothing there in front of that, right? It's blank. That's direct. It means we're talking about address. If we put the ampersand there, it means indirect. that R0 contains the address. And if we put the hash mark, that's the actual data we're going to move. So you've got those three, and you have to remember, I mean, you just have to put it into memory because it will show up on the final, what happens after these following four instructions. Right there. You'll you'll see a question that looks like that. There. Or I will ask you to write, to add the following numbers that are stored in such and such a location. So where you'll have to, we haven't covered how to do that yet, but you'll have to know these various addressing modes and how they're represented right there. So the number sign there, this means that we're going to move the address 0FE00 into the data pointer. The data pointer happens to be a 16-bit register that's used to point to data for accessing external data in memory in particular. Relative addressing is, these next three basically talk about for various jumps. There's various types of jump commands and relative jump or conditional jumps. A conditional jump means that you don't jump every time. In C, you would use if A equals 0. You do something else. Right? Everybody remember something looks like that in C? Well, that's what the jump 0 command. If A equals 0, then we jump to the else. Otherwise, we do this. Right there. So in this particular case, we've got decrement A and jump not 0 back up there. This simply just goes back and just keeps subtracting 1 from A until it equals 0. Right there. Now there's actually another command that does a decrement and jump of 0 right there. So, but we've got that's a command. It's within 128 and plus 120 right there because it's within the current 8-bit, because we're only going to give it an 8-bit address, right, offset. Now, this particular instruction here looks a little strange because this tells us right here that this command here is going to be a number. 8 bits right there. And what we put in here is a label. And we put the label here. Right there. Now, in this particular case, because this is a relatively small set of instructions, I can tell you that this label is going to be -2 or -1. In other words, jump to the previous instruction. But the assembler, when it assembles the code, will actually put a number in that place. Right there. That's going to be either from -128 to plus 128. But it will put a number in there for you. You don't have to calculate what that number, how many bytes we have to jump back to. But that's what that's going to do is it's going to decrement A and it's going to jump if A is not equal to 0 back to the decrement. So the jump command is going to have jump not 0 and it's going to have a number that's how many bytes up we're going to put that. So if we, for example, have something that looks like this, I'm going to just stick it right over here. We have a label here and we have a decrement. And actually you can't really do this because the jump not 0 is going to follow that there. But let's just say we have some code here and then we do a decrement A and we do a jump not 0 back to here. So it will keep track of how many locations it's got to go back to there. You don't have to keep track to. In this particular case, we're just killing time here. But we could do it, for example, and let me just kind of jump. Oh man, I've got something in my eye here. Okay. Let's say in C, let's say C is 4I equals 0, I less than 10, I plus plus, and you've got some code here, right there. We don't care what the code is right there. This is what you do in C, right? This is just a simple for next statement. In assembly language, this would be a move A 10. Right there. We have some code right here. Now, in this code, we have to assume that we're not going to use A. We can't use A because A contains our counter. And then down here, we have a decrement A, and we have jump not 0, and I'm going to call it start loop. Loop right there. And we call this line right here start loop right there. So this is the same code basically in assembly language. It does the same thing right there. And because what our for next loop does there is it starts out, it loads 10 into I right there, and it subtracts I, actually it loads 0 into I right there. I'm doing it the other way around, but it's the same basic thing. Actually, this loads 0 there, it increments it. I guess if I put this as I is equal to 10, I equal 10, I minus would be the same thing there. In other words, we're counting down. We start I at 10, and then I is equal to 0. 0 right there. In other words, we go down to 0 there. Right there. So this would be the same thing. We start the accumulator at 10. We do some stuff. We subtract 1 from 10 from A, and if it's not equal to 0, we go back to the start of the loop. So you can see the correlation between C and assembly language if you look at something like this right here. And I know that you use for next loops or for loops in C. In BASIC, we used to call them for next loops. For I equals 1 to 10, and then down at the bottom of the loop, we would have next I. Right there. In C, they did away with the next statement, so they're just called for loops. But for us folks that used BASIC for a long time, we'll call them for next loops right there. And Fortran called them for next loops as well. But C did away with that there. Okay. Right there. So that's the relative. Again, these are the same thing. Now, the absolute addressing are used for absolute calls and jumps. Now, a call is a subroutine call. We're going to call a function. In C, you call them functions. In assembly language, we call them subroutines. Right there. The difference between a subroutine and a function is a subroutine doesn't necessarily return a value. In C, a function always returns a value of some type, even if the type is type void. And when you took C, did you learn type void, what that means? Anybody know what type void means? Nothing, right? Void means that it has no return value. So you would declare a function. Normally a function you would declare with a type. And you could declare a function as type void, or you can declare it as an integer, or you can declare it as a byte, or you can declare it as type. And that's what the function returns. In assembly language, we generally don't have a return at there. We know that if we call a particular subroutine, it's going to return the value in one of the registers. We have to keep track because there is no return at there. So, okay. The A call means that you've got 8 bits to work with there. It's a 2-byte instruction right there. The upper 5 bits are not modified, so the program counter up there, the upper 5 bits must be located within the current 2K range. In other words, we can't change the now. doesn't mean it's within 2K, because if the current instruction, this is 8 bits, if the current instruction is F2, 3, let's say 2F, F4, for example, right here, our first 5 bytes are 1110 right there. That's F2 right there. So we can only specify that there. So we have to stay within whatever we can specify within this right there. Now, typically, if you're going to use the A call or the A jump, I don't really encourage using those 2 instructions, because since we don't necessarily know where our code's going to fall in the address space that we're dealing with, we don't know whether it's close to one of these 2K boundaries. I prefer to just go ahead and do the long call or long jump. The only thing you save by doing the absolute addressing is you save 1 instruction cycle, because you're only having 2 bytes instead of 3 bytes, and you're saving 1 byte of memory. Memory is cheap today. In comparison to 1980, memory is cheap. I really don't because quite often what will happen, and I say that quite often because it's happened to me more than once, is that, and I've written a number of projects using 8051 controllers where I've ran into this problem, is that I'll stick a absolute call or jump into my code, I'll make some changes, and then all of a sudden that label crosses that 2K boundary, and if I'm lucky, I have an assembler or a compiler that will, in this case if we're using the A call or the A jump, I have an assembler that will catch it and give me a warning. If I'm not lucky, all of a sudden my code just breaks and it won't work anymore. It jumps to someplace I have no idea where it's going. There. So this is one of those ones that it may work, and then you modify your code, and all of a sudden that label and the call instruction are no longer in that same 2K page right there. Now all of a sudden your code doesn't work anymore. There. I find it easier to just go ahead and use the long. The long, you specify the full 16-bit address right there. Now remember that this is code, that the short jump, the absolute jump, and the long addressing, these 3 jump instructions, addressing modes, they're all within the code segment. So you've got 64K there. These are 16-bit addresses we're dealing with. So you've got the short, which is only going to deal with 8 bytes. That's plus or minus 127, minus 128 plus 127. That's an 8-byte instruction, or 8-bit instruction. The absolute gives you 11 bits to play with, 3 more bits. The long allows you to use all 8 or all 16 bits. Now, the long and the absolute cannot be used with the relative jumping. Any of the relative jumps have to use the short. So if we're going to have a jump, it's got to be within 127 bytes roughly. It's got to be within that there. So that there. Again, this is a long call, timer, interrupt, and it's down here. You see, and if I put a call, timer, interrupt, and I write another subroutine, and timer interrupt is no longer in that same code page, now all of a sudden this doesn't work. There. That's the problem. It works the first time, but then as you modify code, which you always do by the time it's finished, you'll end up breaking it, and you'll spend hours trying to figure out where the problem is. Because the problem isn't in anything you added; it's in the fact that we increase the distance between the call and the subroutine or the destination that there. So it's just a matter. So I just prefer to skip the absolute and just use long. That's just what I prefer. Again, some people will probably come back and give me some example of where you shouldn't do it that way, but I've just gotten burned too many times with code that's just quit working because I added some function there and I crossed a boundary. And again, these boundaries are not, if we look at the absolute, it's the current location plus or minus right here. This is minus 128 plus 128. 127. That's the short up there. We've got a 2-page window with the absolute, but we could be here, or we could be here, or we could be here. Where in that 2-page, we don't know where we're at. Where in that 2K window, we don't know where we're going to end up there. You know, back when we used to hand assemble these, then you would have a pretty good idea. But now that you just dump all this into an assembler, you don't know where in this 2K range that we're going to end up. We could be right here, and we're trying to do a call back only 10 places. It still doesn't work, even though we're only going back 10 addresses. It doesn't work because we're so close to that boundary out there. So this here is the boundary is defined by the upper 5 bits. So the lower 8 bits, 11 bits, we have no idea where we're currently at. Because you got to remember, we're going to add or subtract that 11. We're going to change that 11 bits there. So the upper bits can't change. Right there. Index addressing is probably the most complicated one there. I'm going a little slower than I thought. Up there. This is for use relative from lookup table. We set how far down the table. This is the starting value of the lookup table, and this means get the 8th item in the table. Right there. So we've got this table here. We point to it. The top of the table is our data pointer. Right there. So this is the start of our table, and we want this item here. So this here, this is the 8th location right here. That's loaded into A right there. We put the number A that tells it to grab the 8th location in this table right there. Right there. It's not one that I use very often, but it has one that does have a lot of use. Actually, compilers typically will do this more than we will. Okay, we're going to move into the instructions right here. You know, that there. We've got 5 different sets of instructions. These are actually very quick and very short because we don't have that many instructions. Right there. I'll just kind of point them out here. The arithmetic instructions. This is the entire list of arithmetic instructions. Now notice that it's broken into add. Right here. We're broken down into subtract. Right here. Increment. And decrement. Right there. Multiply, divide, multiply. Divide, and then down here we've got DAA. I'll talk about DAA in a minute here. The add has 2 different flavors of add. These all here are going to look at add, and notice that the adds all use for the most part, they use the accumulator and the results stored in the accumulator. There, and we can add 8. We can add a register to A. We can add direct memory to A, data stored in a memory location. We can add memory pointed to by a particular register, in other words, indirect, or we could add immediate data right there. Fairly straightforward right there. We can also add and incorporate the carry as part of the add. So we would add that there. Now the subtraction always takes into account the carry flag. Now, the carry flag is from a previous addition or subtraction, that if we add 2 numbers and there's a carry out, the carry flag is set. So when we add the next two bytes to it right there, that we don't add the carry right there. And that's the same if we're going to add the number 35 to 79. And I'm working at base 10. This is going to be the number 5, and we have a carry out, right? So this becomes 11. This becomes 11, so we have another carry here at 1. So this is the carry flag right there. That's what we're doing. So we just carry that from the previous addition right there. And that's what these do, is they take into account the carry flag. The subtractions always take into account the carry flag. They're always part of the subtraction. Increment, we just simply add increment. Now notice that none of our arithmetic instructions allow us to use the memory external. That there. So our external memory we cannot add, subtract, multiply, or divide with the memory right there. We have the multiply and divide right here. We multiply A times B, and the result is stored in AB. The upper 8 bytes are stored, can't remember. The upper 8 bytes, I think, are stored in B, and the lower 8 bytes are in A, or vice versa. But they're split between when you multiply and divide A by B. Right there, the result's stored in A. Decimal adjust there takes into account if we have binary coded decimal and we have a carry out, it adds the 6 to it right there. So, because if we were to do this addition here, 79, that's 111101 or 01, and we're going to add 6 to it, 0110 1100. When we do this, we're going to get down here 1111. We get the number, we get F there. Well, F's not a valid number, correct? So we add 6 to it, and we get a 5 with a carry out right there. So then we add that number to over here, and we get a 1, 0, or a 1, a 1, a 1, a 1, a 0, and a 1. That's 111011. That's not a valid number, so I have to add another 6 to that in order to get my 1 here. And then with the carry out. So this does the adjustment for the fact that we're using decimal coded by decimal right there. Decimal coded binary. So these are all arithmetic commands. Logical commands are even simpler. We got our AND, our OR, our XOR. Right there. AND, OR, XOR. Right there. We got clear complement. Right there. This clears a register, just makes it all 0. This does a bit-by-bit complementing. In other words, 1010 becomes 0101. It just does a bit by 1. This does a bit-by-bit. And again, we can do this with any of these locations right there. So these are all up there. We have our rotates. Our rotate simply is going to be rotate left, rotate right. So 10111100. If we do a rotate right, it means everything shifts over 1 bit. So it goes like this right there. That one gets dropped off. 0, 1, 1, 1, 1, 0, 0 right there. Right, something like that right there. In other words, everything gets shifted 1 bit this direction. And then we've got with the carry, which means we do the carry flag as part of our rotate right there. And we can rotate right and we can rotate left. And then swap means all we do is interchange these right there. And these instructions are fairly straightforward right there. How we use them is going to be part of the next part there. Data transfer, this is the only place where we see the code and right here. Everything else I'm not going to spend too much time on there. Move C means that we're going to move it within the code memory block. Remember, we have 3 different memory locations. The move is using the internal memory, the 128 bytes that we got to play with internally. The move C means we're going to look at the code with their code, and move X means we're going to use that external memory right there. So we've got 3 different memory locations that we can look at right there. And then we've got our stack that we can push and pop from, and stack is a temporary memory location. And then we can exchange between 2 places within registers or direct or indirect right there. And I've never used this exchange lower order bytes, where we just exchange the lower 4 bits of two registers right there. So that's our data transfer up there. Boolean is just bit operations. That there. They refer to them as Boolean, but I refer to them as bit operations right here. We can clear a bit. This is the carry flag. Clear a bit. Again, this could be a bit in a bit addressable memory location there, or a special function registers. In other words, clear port 1.0, set port 1.0 right there, complement port 1.0, and port 1, and a particular location or with the carry flag right there, or with again, let's just use the carry flag. Move a particular bit to the carry flag. These three right here are jumps if the carry flag is set, jump if it's not set, jump if a particular bit is set, don't jump if a particular bit is set. If a particular bit is set, then clear it and then jump. So these are all, they call it Boolean variables, but it's bit operations right there. So again, there's not very many of these, and I'll be posting these slides later. And then here's the branching, and this is the last of my discussion today, right there. Actually, it's not the last here. Here's our long calls, or calls. Those call subroutines. These are our return from subroutines. Now, notice we got a special one here, return from interrupt. When we write an interrupt service routine, in other words, something happens, we need to do it there. We got our jumps right there. And we've got short jump, indirect jump, right there. Then we got our jump if A is 0 or not 0. We got our compare and jump if not equal. And decrement and jump if not 0. Right there. Right there. And then we have the no-op. And that's basically it for the instruction set. Oh, the instruction set doesn't take that long, but look at all the various addressing modes that there. So that covers a lot. That there, and really the next thing that I'm going to go through. That there. Let me just bring up the lab here real quick and talk about. This is what the lab looks like. It's already been posted. It's called Blinky. You've seen me do the lab already. It doesn't take that long. That's actually a mistake. That should be 1 point. I changed it everywhere else. That should be 1.0. I think right there. Control the speed using delay. Right there. And then we got assume takes 3 cycles to execute every time. So you've got to make some calculations because right there. Right there, and I'll show you an example of this tomorrow, of what this looks like. But you have to come up with how many times you're going to have to go through this in order to set that. Remember, you're going to have nested loops. When I say nested loops, you're going to have 3 or 4 nested, because one loop you can only load this thing up with 256, and right here that it takes that if we go through this. 1,000, that means we're going to have up there. This is blinks per second. That's a very high number of blinks. In order to get down to half a second blink, you're going to have to go through this a couple million times probably. That's there. So I can tell you right now, right off the bat, it's three machine cycles per instruction. If you're making that assumption, right there. So you're looking at right here. It takes 3 cycles to execute every time. Your one cycle is 2 million. You do 2 million cycles a second. So if you don't have a delay, then it's going to take you roughly almost 667,000 blinks per second without the that there. So you'll have to that there. This is the basic format you're going to use. This just simply says that's 8051 code. That's telling the compiler right there. This is the right there. You'll include, this is wrong. I didn't fix that. That should be 850 right there. And then you're going to green light equates it. Oh, this is not the one I uploaded. The one I uploaded, I think I fixed that there. Nothing's been changed here. See, again, this is blank. It's a segment we're putting in the code. It's going to be the code. Switch to our register bank is using bank 0 right there. We're telling it to use register bank 0 right there. This is how we tell it. Switch this to the code so we can specify which bank is 0. We turn off our watchdog's timer. This is where you're going to put your code right there, right here. In this turn, and I've got a couple of might jump. This is mess up, but this is something. Actually, you know what I'm going to do? Let me. This is the actual code that you'll be looking at tomorrow, right there. You see, there's the include. Green light is port 1.10. There's our C code at 0. Long jump to main. Here we're setting up a blank as a register segment using 0. Turn off our watchdog timer. We enable the crossbar. We set up port 0. We'll talk a little bit about this tomorrow. Here's my loops, and I don't know if these loops are right, but all we do is we go through our loops. This is an infinite loop here. It goes to, this goes back to loop 2. This just keeps looping forever right there. And we just change the LED. And this particular one, I've been playing with this. You'll see it in more detail tomorrow. I'm just going to plug this in without doing anything with it. And you can see the LEDs blinking, so right there. So I mean, I can recompile this in there, and then, but I can control the speed by the number of times that I got this going by 6. Again, you're going to have to play with this. Let's just set this at 2. You can see how slow this is blinking. And you can see I actually speed that up right there. You can see it blinking. Go back and let's set this to say, I'm going to set this to a really long number here. And I did a really long number. You can see it's blinking at a very slow rate. I changed that up there. So by just changing that there, but this is the basic code that you're going to look at there. But you're going to have some other things I'm going to be asking you to do too with the lab up there. So that's what you're going to see. But again, you can see that I'm using the basic instructions here, right there. This here, I'm writing a couple of numbers to the watchdog timer. We'll go through that before we'll do the lab tomorrow. I enable the crossbar. I'll talk a little bit about that tomorrow. This is all setting up the special function registers is what this is doing. This is turning off the watchdog timer. This is enabling the crossbar and setting up setting that up. And this is setting up the ports. It's digital I/O ports right there. Right there. Right there. The modes right there. And this is just my delays right there. That's just my delays right there. Right there. This actually is what turns my LED on and off. That just complements the bit. And this just repeats the cycle right there. So, all right. With that said, I think it's time to stop.